Okay, so what I want to talk about now is a final type of scoping that is fairly unusual, but does appear in some programming languages, and that's called dynamic scoping. So the way dynamic scoping works, like the big idea is that if you refer to a variable in a subprogram and it wasn't defined in that subprogram, you go back to the most recent subprogram that defined that variable, and that's the variable definition you use. So that's different than being nested. It's only the value of the variable, the definition, the location of the variable is based on just going back through activation records to find the last place that a variable was defined. So let's take a look at the code that we have over here on the left. So we have a main program which defines a V and a U, and we have a subprogram 1 that defines a V and a W. We have a subprogram 2 that defines a W and X. We have a subprogram 3 that defines an X and a Z and does a calculation using U and V. Neither U nor V were defined in sub 3, so they're defined somewhere else. Where U and V are used when you use dynamic, are located when you use dynamic scoping depends on the order of subroutine calls that gets us to subroutine 3. That's how this works. All right, so let's take a look at, I'm just gonna get rid of the highlighting that I just did. Okay, so let's take a look at an example. So we've got a situation here where main calls sub1 calls itself, the second call to sub1 calls sub2, and finally we have sub2 calling sub3. Now the question is, where is this U defined and where is this V defined to do this calculation for X? All right, to answer that, what we can do is we can look at the activation records for all of the calls to the various subprograms that make this work. So over on the right, you can see the activation records. So if I'm going to go back again and do this again. So if we have main, well, here's the activation record for main, and we've defined two variables, U and V here. All right, main then calls sub1. Well, here's the activation record for the first call to sub1, and sub1 defines a local W and a local V. Sub1 then calls itself, so we have a second activation record for sub1, which also defines a W and a V. Sub1 then calls sub2, so we have an activation record for sub2, which defines an X and a W. And then finally, sub2 calls sub3, which has an activation record for a Z and an activation record for sub3 and defines a Z and an X. Now we can answer the question, if X is equal to U plus V, where does that U defined and where is that V defined? So what we're going to do to find the U and the V is we're going to start at the activation record for sub3 and follow the dynamic link that gets us back to the activation record for the caller to sub3. And we're going to be looking for that U. Well, the U is not defined here in the activation record for sub2, so we're going to follow it back again and look at the activation record for sub1. Okay, we didn't find the U, so we're going to keep going back, follow this activation record. We haven't found the U. We'll follow back to this activation record, and we finally found the U. So the U here is the U that was defined in main. All right, we're going to follow the same process for V. So I'm going to erase these. Good sound effects for erasing, by the way. All right, so we're going to look for V now. So it's not here. So we're going to follow back to this activation record for sub2, which called sub3, and it's not there. So we're going to go back again. and we get to the activation for the second call to sub1, and we see that V is defined here. So this V is the second call to sub1. Okay, so that's one example of how dynamic scoping can work. There's another example of how it can work as well. This involves, if you look at this, this involves a lot of processing, right? Every time I have a variable reference, at runtime, I have to run down these dynamic links and look up and check to see if that variable is defined in the previous activation record and just continue down the chain. So that could be very computationally expensive. So there's another way to do it called shallow access. So the way shallow access works is that you create a stack of subroutine of links to subroutines for every subroutine that gets called, and you use that stack of subroutine calls for each variable to figure out where the last definition of a variable was made, which subroutine the last definition of a variable was made in. And so I want to show you how that works. So we've got the same code again, and we've got the same process, all right? Main calls sub1. Okay, so first of all, we're going to start with main. So main defines the variables v and u. So we're going to put, for the variable u, push main onto use subprogram stack. This is kind of just a mechanism that the program at runtime can use to keep track of variables and where they were last defined. All right. Also, v is defined in main, so we're going to push main onto v stack. At this point, the two sub1s above v, they don't exist yet. So things don't exist until I highlight them. All right. Now, we're in sub1. Sub1 defines v and w. So for v, we're going to push sub1 onto v stack, and w, we're going to push sub1 onto v stack. So at this point, the stack consists of only, this tracking mechanism only consists of three variables, u, v, and w. And we only have main for u, main and sub1 for v, and sub1 for w. All right, sub1 then calls sub1 again. And so for this v, we're going to push another sub1 on the stack. And for this w, we're going to push a second sub1 on the stack. Now we have sub1 calling sub2. Well, sub2 defines w and x. So we're going to push sub2 onto w stack, and we're going to push sub2 onto x's stack as well. All right, sub2 now calls sub3. So we're going to push sub3. So sub3 defines x and z. So we're going to push sub3 onto x's stack and sub3 onto z's stack as well. All right, so now we're at the point where we have x equaling u plus v. All right, so where does this x come from? Well, we go to x's stack, and we see that at this point, sub3 is at the top of x's stack. So that is where we go for the definition for x, sub3. That makes sense. All right, what about u? Well, we go to u's stack, and we see that main is the last place where u is defined. So that's where u is going to get its definition from main. And then finally for v, we go to v. V's quite busy. There's 3 different subprograms that are on v stack, but the top one is the second call to sub1. So that is where we get the definition for v. This is way more efficient than this, but they're both mechanisms that a programming language could do to implement dynamic scoping.